So back in chapter 7.1, we studied solving systems of equations using substitution. Here in chapter 7.2, we're going to cover another technique for solving systems of equations, the elimination technique. All right, elimination is another technique that is often used in solving systems of equations. Here are your steps for the method of elimination. 1. Obtain coefficients for x or y that are the same or differ only in sign by multiplying all terms of one or both equations by suitably chosen constants. 2. Combine the equations using addition or subtraction to eliminate one variable and solve the resulting equation. 3. Back substitute the value obtained in step 2 into either of the original equations and solve for the other variable. 4. Check that the solution satisfies each of the original equations. So with elimination, your main goal is to combine your equations using addition or subtraction to eliminate one of the variables. Now, you may have to manipulate one or both of the equations in order to get a variable to become eliminated. However, that is not necessarily always going to be the case. So let's look at a few examples here where we can use elimination. Solve the system using elimination. Here we have 3x minus 5y is equal to 2, and 2x plus 5y is equal to 13. Now, there are two reasons why this particular problem is a good candidate for the elimination technique. One, if we look here, we notice that the coefficients of y already differ in sign. In the first equation, I have minus 5y. In the second equation, I have plus 5y. If we add those two equations together, the y values are going to be eliminated already. That's reason one why elimination is a good option. Reason two why elimination is a good option is because if you were to try to isolate one of the variables, recognize that you would end up with some ugly fractions to work with. All right. So instead of working with fractions, we can use elimination to avoid that situation. So as we just said, we've got opposite signs of y, opposite coefficients of y. By adding these two equations together, we can eliminate y. 3x minus 5y equals 2, plus 2x plus 5y is equal to 13. And it's easiest just to add these two equations vertically. Notice 3x plus 2x gives me 5x. My y's, they are going to add to 0. 2 plus 13, that is going to give me 15. We end up with 5x is equal to 15. Dividing both sides by 5 gives us x is equal to 3. Now that we have solved for one variable, we can back substitute it into either one of the first equations, either one of these first two equations to solve for the second variable, right? It doesn't matter which one you choose, pick whichever one is easiest for you. All right, so here I decided to plug it into our second equation. 2 times 3 plus 5y is equal to 13. 2 times 3 is 6. That gives me 6 plus 5y equals 13. If I subtract 6, I get 5y is equal to 7, which tells me that y is equal to 7 over 5. And once we identify x and y, we want to write our final answer as an ordered pair. 3, 7/5 is my final answer. We can verify the solution by plugging the ordered pair into each of the original equations, and doing so will make each one of our original equations true if we have the correct answer. We can also verify our answer graphically by graphing both of our lines in this case and finding the intersection point. Doing so, we recognize that the intersection of these two lines is indeed at 3, 7/5. All right, let's try another one. Solve the system using elimination. So in this case, again, two reasons why elimination is going to be a good option. We have 5x plus 2y equals 10. 5x minus 3y is equal to 5. Reason number one this is a good option for elimination is because the coefficients of x are the same. I've got a 5x here in the first equation and a 5x here in the second equation. Because the coefficients of x are the same, we can eliminate x by subtracting the two equations. So I can take these two equations and just subtract them vertically. 5x minus 5x, well, that's just going to give me 0. I have 2y minus a negative 3y. Now be careful when subtracting because you must remember if you are subtracting a negative, that turns into addition. Okay, 2y minus a negative 3y becomes adding 3y. That's 5y is equal to 10 minus 5 is 5. 5y equals 5, which means that y is equal to 1. Again, once we isolate one of the variables, we can back substitute it into either one of the first equations that we see here and solve for our second variable. I have decided to plug it back into the first equation, 5x plus 2y. That gives me 5x plus 2 times 1 is equal to 10. That means 5x is equal to 8, and x is equal to 8 over 5. Again, we write our final answer as an ordered pair, 8/5, 1. We can check our solution by plugging in those values for x and y into both of these original equations, and it will make both of them true. Graphically, this is also the intersection point of our two lines, 8/5, 1. Let's try a couple more here. All right, solve the system using elimination. 2x minus 3y is equal to 3, and negative 4x plus 6y is equal to negative 6. Here, we can multiply the first equation by 2 to obtain opposite coefficients of x, and then combine with addition. So right off the bat, none of our terms are going to be eliminated if we add or subtract the equations. However, elimination is still going to be our best bet because trying to do substitution will give us ugly fractions. Again, try to avoid those fractions if at all possible. But we can multiply this entire first equation here by 2. Doing so gives us another form of the first equation. That's 4x minus 6y is equal to 6, which we can now combine with our second equation here. If we combine those with addition, we have 4x minus 6y equals 6, and negative 4x plus 6y equals negative 6. 4x plus a negative 4x, well, those are going to eliminate and become 0. Negative 6y plus 6y, well, that actually eliminates as well. And 6 plus a negative 6, well, that equals 0 as well. We get 0 equals 0. So this is a little bit interesting here. What does this mean? This actually tells us that we have infinitely many solutions. Okay? The two lines in this particular case coincide. They are identical. Any point on the lines will be a solution to the system. So anytime you are solving a linear system that results in a true statement, okay, this right here, you try to solve it, you get a true statement. 0 equals 0 is a true statement. That means that there are an infinite number of solutions. And if you were to try to graph each of these lines, you would actually recognize that they're the same line right on top of each other. Notice I got a blue line and a red line. Blue line over a red line gives me a purple line. Okay, all right, so we actually have the same line drawn twice. We have infinite number of solutions. A few more here. Solve the system using elimination. All right, so we look at this system. 3x plus 11y equals 4. Negative 2x minus 5y is equal to 9. We don't want to use substitution because we're going to end up with fractions. Instead, we can use elimination. That being said, we're going to have to manipulate both equations in this case to get one of our variables to cancel out. Now, it doesn't matter which one you try to get to cancel out. If we want to get x values to cancel out, that means we are going to multiply the first equation by 2 and the second equation by 3 to obtain opposite coefficients of x. That way, when we combine them with addition, our x's are going to be eliminated. So we take this first equation, we multiply the entire thing by 2. That gives us 6x plus 22y is equal to 8. We take our entire second equation, we multiply it by 3. That gives us negative 6x minus 15y is equal to 27. We can now combine those using addition. 6x plus a negative 6x, well, those are going to add to 0. 22y plus a negative 15y, that's 22y minus 15y, leaves us with 7y. And we have 8 plus 27 gives us 35. 7y is equal to 35. When I divide both sides by 7, we end up with y is equal to 5. Now that we have one variable, we can back substitute it into either of these first two equations. Again, it doesn't matter. I decided to choose the first one. 3x plus 11 times 5 equals 44. Well, 11 times 5, that's 55. And if I subtract that to the other side, 4 minus 55 gives me negative 51. 3x is equal to negative 51. I divide both sides by 3. Dividing both sides by 3 gives us x is equal to negative 17. Our solution, negative 17, comma, 5. Again, we can check our work, verify our solution by plugging the ordered pair into each of the individual original equations, or check our work graphically. If we were to graph each one of these lines, we notice that they do indeed intersect at negative 17, comma, 5. All right, their intersection point is the solution to the system. Okay, couple more here. Solve the system using elimination. All right. Well, again, why do we want to use elimination in this case? Well, if we try to use substitution, we are going to end up dealing with some ugly fractions. So, which variable do we want to eliminate? Well, if I'm looking at my x's here, I notice if I multiply this first equation by 2, I am going to obtain opposite coefficients of x, which means when we combine them, the x's are going to disappear. Let's multiply this entire first equation by 2. That gives us 12x minus 10y is equal to 6. We can now add this equation here with the second equation. And in doing so, we get 12x plus a negative 12x. Well, those are going to cancel out. The x's are eliminated. Negative 10y plus 10y, those actually end up being eliminated as well. We get 0 is equal to 6 plus 5. Well, that gives us 11. All right, so this one's interesting here. We end up with 0 is equal to 11. What does this mean? Well, this is actually a false statement. 0 does not equal 11. This means that we actually have no solution. Okay, and because both of these are linear equations, we actually are dealing with two lines. If we have two lines, this means graphically that they don't intersect if there is no solution to the system. Therefore, the two lines are parallel, meaning that they do not intersect. There is no solution to this system of equation. All right, anytime you are solving a system that results in a false statement, this is our false statement here, 0 does not equal 11. If you get a false statement, then there is no solution to the system. And again, we could verify our answer graphically here. If we were to graph each one of these lines, we do indeed see that they are parallel. Parallel lines do not intersect. Therefore, there is no solution to our system. And there you have it. That is solving systems of equations using elimination.